Hi everybody, welcome to our most unusual ICD TWF repair video. In the last few years, I've shown on my channel all the computers and peripheral repairs and some projects, or also arcade-related repairs and projects. However, as you may know, ICD TWF is in fact an amateur radio call sign that I hold since 2007. I've been licensed since 1995. And I had different call signs in the previous years, so in a distant past I repaired quite a few transceivers and radio-related equipment for my own station and for other operators too. I've worked on some old vacuum tube equipment as well as on the old solid-state gears of the 1980s and 1990s. However, I often found that working on this kind of electronic devices is a very time-consuming task. So I started soon declining to take repairs of other people's equipment. Of course, not very often, there are some good friends that can convince me to make just a last repair on some very special equipment to them. I think this kind of repairs can be very interesting from the analog electronics point of view. But if you are one of my usual viewers only interested in old computers and arcades, please have a little patience. There will be lots of the usual videos and projects coming soon. The transceiver I have on the bench now is a Kenwood TS-180S. It has no continuous coverage. That means that it will transmit and receive only on some of the amateur radio bands on medium and short waves. It lacks the shortwave bands that were assigned for amateur radio use in 1979. In this web page you can see some of its key features. It was, of course, made in Japan starting in 1979 and discontinued sometimes during the 1980s. So, here is our transceiver. Let's have a quick look on what its problems look like. First of all, we can hear this continuous tone. Although it seems stopping on some frequencies. Some of the bands seem also completely dead. Look at the frequency counter that shows only dots. So I'd say there are a few different faults at least. Luckily, it's usually possible to find the complete service manual of all these old transceivers. However, you will soon discover why I decided to not accept very often repairs like this one. When repairing electronic devices, one good approach is usually to assess the symptoms, then studying how the device is supposed to work, then starting probing in the parts of the circuit that are likely to be involved with the faults we observe. In this case, for example, we might want to study the frequency conversion configuration of this particular transceiver and look for any incorrect value or level or bad part or whatever else. However, in the case of a moderately complex device like a multi-band transceiver, this approach would be, in my experience, quite ineffective. We would follow issues after issue on different circuits without really understanding what's going on and why. Unless, of course, we are very familiar with a particular device and we have already repaired lots of them. I am instead using a method that usually works for me when I'm servicing a device like this, or an even more complicated one like, for example, one of the HP test instruments I have on my lab. I usually go on the adjustment or alignment section of the service manual and start from the beginning. As soon as something cannot be adjusted as required, I know I have found a problem, and I know I need to fix that problem before going further down in the list. So here's the first step of the procedure. We just need to check for the 8V supply value and adjust if it's necessary. This is the voltage regulator board, and I have connected both a multimeter and the oscilloscope, just in case. Let's power on and check. Oh, that's way too high. Let me turn it off. This circuit is not working for sure. So I removed the 4 screws holding this PCB and its heatsink, and I'll troubleshoot it separately. This is the board schematic from the service manual. This circuit generates 3 regulated DC supply rails, 8V, 8.1V and minus 6V. The only adjustable one is the 8V rail by means of VR1. But if this circuit was working well, then it would be not possible to have the full input voltage at the output, even when VR1 was adjusted to one extreme. The first issue with this board is that it has many cracked solder joints. Some of them are clearly visible in this picture. This is not a big surprise since this circuit dissipates a lot of heat, and in general the solder quality of these old Japanese radios was not spectacular. So I have resoldered the whole PCB and then cleaned all flux residues. Now I can test the board by powering it outside the radio. However, the 8V regulator circuits are the low dropout kind of linear regulators. They can be recognized because the output is taken from the collector of the pass transistor. In this case, they are Q4 and Q9. Usually, these kind of regulators have a low-value resistor between input and output. In this case, they are the 47 ohms R6 and the 18 ohms R7. Whenever we need to test one such regulator, we have to remember that they need a minimum current load before they start regulating, and this minimum current value depends on the value of the bypass resistor we have seen before in the schematic. It's easy to calculate this minimum load current. Basically, it's the current that gives the full input to output voltage drop on the bypass resistor. So, by applying Ohm's law on the values we have on this 8V regulator, we can calculate a minimum load current of 123 mA. To stay on the safe side, I will choose a load resistor to sync about 150 mA. The load resistor value can be again calculated with Ohm's law, and it's about 53 ohms. It also needs to dissipate at least 1.2 watts of heat. With a quick search in the power resistors box, I found this old 50 ohm 5 watts wire wound resistor that's just perfect as our 8V load. The last thing I need to do is to jump these 2 ground pins on the input connector, since this link will be made inside the radio, but I will be using a bench power supply instead. So here is the test setup. This is the power supply input. The ground return is connected to the heatsink. This is the load resistor, and it is connected to the 8V output test point together with the multimeter. So let's turn it on. Well, the voltage is already close enough. Let me bring it down to 8.0 volts. Now I want to check that there are no loose connections anymore, of course using a non-conductive stick. Okay, so far so good. Let's now check the other 8V rail. As before, I need to calculate the value for a suitable load resistor to allow the regulator to operate correctly. This time, the bypass resistor is 18 ohm, so repeating the same steps as before, we get a load resistance of about 25 ohms that dissipates 2.6 watts. Now I have added the new load resistor, two 47 ohms resistors in parallel. The multimeter probe goes now on this other test point. 9.4 volts looks a bit too high. This regulator has no adjustment also. I want to try sinking more current, so this time I'll use an 18 ohms resistor. Almost no difference. I think it's time to get back to the schematics. So, the test point says 8.1 volts, but look at the voltage reading circled in red. It's on the same node of the test point, but it's 9.2 volts, so we cannot obviously have two different voltages on the same node. So what's the correct one? D5 is a WZ040 Zener diode, which is 4.0 volts nominal, with 500 mW maximum power dissipation. So, the 4.8 voltage reading at Q8's emitter plus the 4 volt Zener would already put the output at 8.8 volts, and not 8.1 for sure. Another clue is, however, the voltage at Q8's base, indicated as 5.4 volts. This voltage is obtained with a single voltage divider from the output voltage, and we can ignore the small Q8's base current that is surely much smaller than the about 9 mA flowing into the voltage divider. So, if we do the math on the divider, we find that the correct base voltage indicated in the schematics can be only obtained if the output voltage is 9.2 volts and not 8.1 volts. For instance, this also means that they used probably a 4.4 volts Zener diode, or they selected the higher voltage ones. In any case, the regulator circuit is working fine in my opinion. This also illustrates another very common issue of all these old amateur radio transceivers. Their schematics and service manuals always have a few mistakes here and there. Now it's time to reinstall the regulator board back on the radio and see what happens. There is still the continuous tone, even if now the 8V rail is correct. But the tone eventually disappears. And sometimes it starts again at power on. Interesting. The dead bands are still dead. It seems not much progress so far. Before going on with other alignment steps, however, I've completely forgot to test the third and last voltage rail produced on that regulator PCB. It is a -6V DC rail obtained with a little switching circuit. Q1 and Q2 form an oscillator, and they turn on and off in alternating periods. The capacitor C5 is connected either to 13.5 volts when Q3 is on, or to ground when Q2 is on. Of course, Q3 and Q2 cannot be on together at the same time, because Q3 is on only when also Q1 is on. The alternating current going to C5 is then rectified by D1 and D2. So C6 charges with a negative voltage with respect to ground. D3 is a 6V Zener diode that clamps the output voltage to minus 6 volts. Now I can see a possible issue with this circuit other than a randomly failed component. But first let's check if this is working as expected or not. Let's now monitor the minus 6 volts supply. Notice how the voltage decays slowly after power off. If we now allow the voltage to drop all the way to zero, and then power on, here is the tone. Notice how it stopped when the negative rail started building up again. I think here we have an issue with Q1 and Q2, and the fact that Q2 became quickly hot after power on is another good clue. So I first removed Q2 and tested its HFE, which is the current gain. The value of 20 is indeed too low to be good. Both Q1 and Q2 are 2SC945A marked with the QHFE rank. So let's look at its datasheet. The QHFE rank should indicate devices with a gain comprised between 135 and 270. In any case, no such transistor should even show a gain less than 50. In fact, one of my spares, also marked with the Q rank, shows a gain of 262, right at the top of the possible interval. So what about Q1? Again, we find a very low current gain, surely outside the Q rank interval. And here is another of my spares that's going to replace Q1. This one is even showing an higher gain than the top of its rank. Now, to illustrate what's the problem in this circuit, I need first to replace both Q1 and Q2 and take some oscilloscope pictures. By the way, with the new transistors, the minus 6 volt rail starts right at power on without issues. I've not reconnected the rest of the board as I need to do some other modifications to it. Let me now explain why Q1 and Q2 failed. What you see in the screenshot is the base voltage of either Q1 or Q2, as they are identical. I'm using the B scope channel and the B voltage selector is at 1 volt per division position. But since I'm using a divide by 10 probe, then we are at 10 volts per division. The top flat part of the waveform is actually at 0.6 volts, but looks almost at zero on this scale. This is the interval when the transistor is on. At some point the base is pulled negative to about minus 10 volts and the transistor turns off. Then the base voltage slowly rises again and the transistor switches back on when it reaches 0.6 volts again. The problem is that most transistors can only withstand about minus 5 volts from base to emitter before the base to emitter junction goes into reverse breakdown and the transistor starts damaging. This fact is also clearly stated on the fine book The Art of Electronics. And guess what the base to emitter breakdown causes? A permanent degradation of current gain beta, which is another name for HFE. The book also suggests that a good way to protect the transistor is to add a diode in parallel between emitter and the base. Of course, such a circuit modification should be first evaluated to see what other variations are needed to make the original circuit behave as it was intended. In this particular case, adding the diodes on both transistors will for sure change the oscillation frequency of the circuit, but since the only purpose of this oscillator is to have an alternating current going through C5 to be rectified, then the actual frequency is of no importance at all. So I have added two small 1N4148 diodes on the bottom of the PCB, and I'm going to test again the board to see if it still does what it needs to do. As expected, the Linux 6-volt rail still starts fine right at power on without issues. Let's also look at the new base waveform. Now, the oscilloscope voltage selector is set at 0.1 volts, so together with the probe, the vertical scale is 1 volt per division. The on interval shows a slightly sloping voltage of about 0.7 volts, and in the off interval, the added diode limits the reverse voltage to a safe level of less than -1 volt. So it's time to connect everything and see what happens. Okay, not on anymore. The -6 volt supply starts correctly. All the other issues, however, are still present, but I'll show in another video how they have been fixed. So this is all for this episode. I hope it was an interesting journey into unusual electronics of the past. If you have any question, please use the comment section below. I hope you return to the channel for the next repair videos, and for now, thanks for watching.